Okay, thanks everyone for joining the call. Today we're going to go through the Lay2 PW-SDK checkpoint 1 for their grant project. Frank is going to be presenting from the Lay2 team to review the update and progress. And Jordan will be watching, reviewing, and asking questions at the end from the Nervos Foundation side. So without further ado, Frank, please take it away.
Okay, thanks, Ben. Hello, everyone. I'm Frank from the Lay2 team. I'm very happy to share our progress with all of you. First, I want to make a small introduction of us. I am Frank, and I'm in charge of the product and also the front-end development. The other member is John. Can you say hello to others, John? Hello? You there?
Oh, he's muted.
So yeah, never mind. John is in charge of the R&D and the backend development. Yeah, and for those who are not familiar with our project, PW-SDK is for the CKB developers of the dapps developers, but it's not. It's quite different from the ordinary SDKs, as it not only let developers produce the CKB dapps, but also empowers those dapps to run in other blockchains infrastructures, such as the Ethereum wallets or even EOS wallets, any mainstream blockchain wallets. Okay, so let's first record the checkpoint of this stage. There are three parts of the checkpoint. The first is the PW-lib, which is the cryptography primitives library of the PW-SDK. And we will have the Kashak 256 hash algorithm support. The second part is the PWLock. We will support the Ethereum signature method. This means the default or the common method called personal sign. And we will support the EIP 21712 signature method, which is called the sign type data. And we will make PWLock be able to deploy with the type ID. The third part is the PWCore. This is the front-end JavaScript SDK of the PW-SDK. And at this stage, we will finish the API design. The PW-lib, the Kashak 256 is the hash algorithm, the default and the only hash algorithm used by the Ethereum. Like the Blake2B algorithm in CKB, which is also the default one, but not the only one. This is an advantage of CKB. We can have a lot of cryptography primitive libs here, and we can replace the default algorithms. This is why we can make the PW-SDK happens. Yeah, and the Kashak 256 algorithm is used in PWLock to generate Ethereum address. So I will see some. Okay. Used in the PWLock to generate Ethereum address with the pub key recovered from the signature in witnesses. I know this is a bit wrong, so let's take this apart. How to decide whether a cell can be unlocked? We have to check whether the sender of the transaction owns the cell. So in the CKB, we have args in the lock script, and we have to retrieve the proof from the witness to compare with the args, right? So in PWLock, the args is the Ethereum address of the sender, and the signature in witnesses is signed by the sender's Ethereum wallet. So we can recover the pub key from the signature with the ECDSA recover method. And then we will generate the Ethereum address from the pub key with the Kashak 256 hash algorithm, then we can compare the address in the ARCs with the address we generated. So this is when Kashak 256 take place. Okay, there are 3 APIs, and the first one is the init API, which will initialize the context of the calculation. The second one is update. You can consider this as an append function. You can invoke this function again and again and append all the messages you want to calculate the hash with. And then when you finish with the appending, you call the final function and you can get the final result of the hash calculation. Okay, the second one is the PWLock. There are 4 features here. The first is the personal sign. This is the default signature method of Ethereum. And if you are familiar with this method, you will know that there is an ugly prefix prepended in with your message to sign. Yeah, we can see there. Can you guys see my cursor? Can you see this? Yeah.
Yeah, we can see it.
Yeah. This part is the prefix. Is the hard-coded prefix, and the 32 means the length of your content to send. Yeah. So a lot of questions being made about this. They are asking, how can you do this? Do you know their prefix, how to handle this? We will go into detail later. The second one is the sign type data method. This is a human readable signature standard defined in the EIP 712. And we support the latest version, which is the version 4. And the third one is that can be deployed with the type ID. The type ID, the feature can make the upgrade of the log script won't mutate the addresses. This means when I upgrade the logic or fix a bug, you can keep your address the same. Maybe you have questions why it will change. Yeah, we will talk about this later too. And the last one is the anyone can pay lock. Yeah, this is also a question that had to understand why this is needed. Yeah, this is about CKB's feature, the character. Yeah, so with the anyone can pay lock, you can receive one channel or just a pure UDT from anyone. The pure means that the sender won't need to provide any CKB for store for the UDT storage. He can just send you 10 USDT instead of 10 USDT with 100 CKB. Okay, first let's go to the personal side. Let's see some actual usage here. The first screenshot shows the signature procedure in the P-Wallet, which is, you can consider that P-Wallet is the first dApp that uses the PW-SDK. This is the P-Wallet running in the IM token, and as we can see, the pop-up window of the signature is a native window. It is from the IM token app, not from the JavaScript. This means the signature is has a native security level. We can see the content of the signature is just a nonsense hex message. Yeah, this is secure, but we think we can go further. So let's see a small video. Yeah, this small video shows an interesting procedure that when you make a security transaction with the P-Wallet, you can just approve this transaction with a hardware wallet. This hardware wallet is called IMK. It is produced by the IM token. It's a Bluetooth hardware wallet. So we can see CKB already have hardware wallet support. Yeah, this is, I think this is the most amazing part of CKB. We don't have to build it from ground. Yeah? We just borrow the mature infrastructures from other blockchains. Okay, then we see some code here. First, we see the front end. It's in the default signer. Can you see the code clearly? Maybe I should.
Yes, I can see it pretty well.
Yeah, I can zoom this. Yeah. Okay. The default signer, we can see it's not different from when you are calling this method from Ethereum dApp. It's completely the same. You don't have to tweak the implementation for PW-SDK. Yeah, it's the standard send async method. Okay, let's say the lock script. We can see there is a verify SecP256 sec hash OR method. This is called in here, the verify signature function, and we can see here. The first one, verify signature with personal hash. We can also see the ugly prefix here. Yeah, hard coded. As they are hard coded, so I think this is okay. And we can also see the usage of the Kashak function. Okay, second one, sign type data. This is the standard from the EIP 712. First, the extra usage, we can see there is a screenshot of the pop-up window with the MetaMask notification, right? And there is a main Ethereum network here, but this doesn't matter. The first thing we see is the ckb.pw domain. This is the domain of the P-wallet. So this will avoid some phishing site. If you check it carefully, you will see the domain is right. And then we can compare the signing message with the last one in the M token. You can see the content in M token, which uses personal sign, is just a nonsense. Blah blah blah, and the signature here is readable. You can see the transaction hash. You can see the transaction fee. You can see the total capacity of the input cells, and you can see all the outputs listed here. The first one, the address is the amount is 100 CKB, and the second one is a change cell, and we have tried for 100 outputs in single transaction. That works well. Okay, by adopting the EIP 712 method standard, we can provide more clearly information for users, because the user can know what they are signing, right? They are not just close the eyes and sign the signature. They have the clear idea of what they are sending, who he is sending the asset to, and how many CKBs he is sending to him. Yeah, I think this is very important. So let's go to the code. You can see not far from the first one, this is the calculate type data method. And this method is a bit longer than the other one. Yeah, because type data is quite complicated to assemble. Yeah, it's quite long. So is the front end, but the front end is not so different from the default signer, right? The only thing here is that you have to build the time data first, and the build function is, this is bigger. We have to go through every output and to calculate the results and fill the results into the template like this. So we can see the message we have sent in the pop-up window is not just some message I can fill up randomly. This is all these results are calculated from the transaction itself. So you can trust that what you are sending is what is actually sent to the blockchain. Sorry for the babies crying. As we can see in this verified signature method, these two verify method is quite close. This shows the procedure that when we first check the personal sign message, if the personal sign hash is right, then the lock script is successful. And if the personal sign failed, we will check the type data again and return this result as a final result. This procedure can be shown more clearly here. The left part is the default lock of the CKB, and the right part is PWLock. We can see the first few steps is exactly the same. The first difference is when we calculate the hash result, the default one uses BLIK2B, and the PWLock uses Kashak 256. And the second one is there is an extra step to calculate the personal hash before we cover pub-k, because this is the procedure when you use the Ethereum, when you want to get an Ethereum address. The third one is this part, the BLIK 160 hash. As the default lock, it retrieves the first 20 bytes of the BLIK2B hash, and in Ethereum we will retrieve the last 20 bytes of the Kashak hash. Yeah. And the last difference is there is an extra step, as we shown before, to check the EIP 712 type hash. Okay. Then the type ID and ACPL. ACPL is short for Advanced Campaign Lock. And here I want to make a special thanks to Xuejie, because the two features are designed and developed by him. I want to say this quite excellent job, and your jobs makes it a lot easier for developers like us. Right? And the first one, type ID. This enables upgradability of lock script without breaking addresses, as we talked before, and we can see some details here. As we all know that the address concept, the concept of address in CKB is something different from like Ethereum. Your address actually is the lock script. The lock script here. This is the actual address. If you go into the RFC of the address, you can see that every address is calculated from this structure. So what if I upgrade the code in the lock script code cell? Of course, the code hash will change, right? If the code hash changes, the lock script changes and your address changes, which means the assets in the former address will completely gone. You cannot retrieve again unless you deploy the former version of the code to the blockchain. Yeah. So how to solve this? There comes type ID. As we can see in this diagram, the type ID is the type is not null anymore. It's an upgrade. This is the code of the type ID. And if we upgrade the code cell, the data will change, but the type will remain the same. So the code hash, which is calculated from the type, will remain the same. And the lock script and also your address will keep constant. Yeah. So this solves the problem. And another thing I want to point out is we used a multi-signature lock for the code cell. This improves the security of the cell, and this make it possible to, to involve community governance of the PWLock in the future. And the ACPL, anyone can pay lock. There is a minimum amount of the CKB transaction, which is 61 CKB, as we have to store some metadata of this transaction. And if you are familiar with the UDT design, the UDT is recorded in the data of a cell. So if you want to send some UDT to others, you have to send the cell that contains the data, right? So you don't lose your UDT only, you lose your CKB along with it. So anyone can pay lock solve this problem. It can let you receive any amount of CKB, even 1 shilling, and we've tested on the former Agram testnet. And you can receive UDTs without asking the sender to provide capacity for storage. Yeah, the details I won't go into details here. You can see the articles, the blog of the ACPL in Xuejie's blog, which is xuejie.space. Yeah. Okay, the last part is PWCore. This is the front-end SDK. It's written in TypeScript. We want to design this and design the API for the developers to build once and run everywhere, because it's already now runs in almost all Ethereum dApp browsers. We've tested, MetaMask, Trust Wallet, IAM token, BitPy, whatever, Kobo. Yeah, a lot of wallets have been tested, and it will run in BTC, EOS, Tron, even Libra, yeah, and of course CKB. When CKB has the dApp browser, yeah. This makes it a lot easier for the developers to, acquire the user bases. Because if you develop a dApp, you want more users to get access to it, and if you use PW-SDK, every user of these blockchains already got the address they needed and got the environment they needed. It will lower the barrier of the user in a big amount. Yeah. The second is when we want to make it simple and flexible, we want to shield the underlying details. We can see some examples here. Yeah, because there is a lot of kind of addresses in PW-SDK. If you're using a Ethereum address, you can use a CKB address. You don't need to transform the address formats with a lot of other APIs. You just new an address instance and passed in the address string and the address type. Then you can play with it. Just like get the lock script hash, get the lock script, and everything you need to, from address is included in this class. And another one is the amount class. This is, I think this is my how to say that? Yeah, I love this design best because PWLock is the front end of PWLock is developed by me, and it's really annoying to play with those the amounts transformations to get a lot of hex strings or to display the amount in some format. So I just wrap all of this into a class called amount. You can use an amount with 1, just a decimal string 1, and tell the class that this is a CKB amount. You can also use an amount called 10,000 and tell the class this is a Shannon amount. Then you can just use the static method called add and add those 2 amounts and just 2 string to get a string that the unit is CKB and with the right pending of zeros. And we can see the result is 1.00100. Yeah, I think this is quite, it makes life a lot easier for the developers. And all the built-in static method is listed below. There have add, sub, greater than, equal, less than, equal, and the equal. Yeah, it's just like the big int class. And we also want to make it flexible, so there are a lot of customizable components here. There are 3 virtual classes. The builder is you can extend the builder to build your own transaction structure, and you can extend the signer to invoke invoke any kind of signing signature algorithm. Just like we said, the personal sign or the sign type data, maybe the signer from the US, Bitcoin, etc. And the collector, this is I learned this from the Xuejie's another project called CKB JS token. You can define a collector and collect the unspent sales you needed in the transaction. Either you can use the IPC collector, which is not recommended in the production area because this will be quite slow. And you can make a collector that connects to your backend server and get the sale from a catch server. So this is the whole designing, the whole API document is listed in the README document of the PWCore in our GitHub repo. You can find all of the repos and the code in the Nervos talk thread. I've listed there. So this will be all of my introduction. Thank you for listening, and any questions?
Yeah, thanks for that very thorough presentation. I just have one quick one. I'd like you to open up GitHub just in a browser, and if you could quickly just run through the structure, just kind of pointing out at a high level each of the checkpoints that you were supposed to do, and just kind of point to the file just for the record so that anybody can, who wants to review it by themselves can do it.
Okay. So the first one, maybe the Kashak 256 is located in yeah, this is in github.com, Lay2 div and PWLock. It's in the C folder, and it's called the kashak256.h. Yeah, this is the Kashak 256 hash algorithm of this one. And the second one is the PWLock. PWLock's it's here. The main logic is in the header file, yeah. So you can find all the functions I've talked through in the presentation in this file, including the personal sign, the EIP 712. And the type ID actually is type ID. Where is the type ID? John?
Okay, CKB cell upgrade.
CKB cell upgrade.
The first one.
Here.
Yeah.
Yeah, this is the type ID code. Okay, and the API design is and anyone can pay lock, which is a bonus. Yeah, it's here. Anyone can pay lock. And the third one is the PWCore. This is just okay, this is the PWCore, and the first version of the API designing is here. There are classes, there are functions, and there are examples. Yeah.
Okay, great. Yeah, that's it. It was a very thorough presentation. Thank you. Ben?
Yeah, great. Thanks so much, Frank, and thanks, Jordan. I think the presentation was great. I think you very accurately and comprehensively demonstrated the checkpoints have been reached. So if there's any questions from anyone else, then please feel free to ask. Otherwise, we can end the review call here.
Yeah, any suggestions or questions are also welcome in the Nervos talk. You can just post it under our thread. Yeah.
Great. Okay, thanks, Frank. Thanks, Jordan.
Thank you, everybody.
Thanks, everyone. Cheers.
All right. Thank you.